Hi friends, in this session we'll discuss about the languages which are not regular. In the previous video of regular languages, we discussed that every finite language is regular. Some infinite languages are regular. Not all infinite languages are regular. And the regular languages are closed under union, concatenation, clean star, complement, intersection, difference, reverse and letter substitution. Given a language, how shall we show that the language is regular? So the easiest way to prove that the language is regular is by writing a regular expression or designing an FSM or a finite list of equivalent classes or writing a regular grammar or by using closure properties of regular languages. Next, to show that the given language is not regular, the easiest way to prove that a language is not regular is by using pumping theorem, which is based on pigeonhole principle. So let us see what pigeonhole principle states. Suppose that a flock of 10 pigeons fly into a set of 8 pigeonholes to roost. Because there are 10 pigeons but only 9 pigeonholes, you can see here 1, 2, 3, 4, 5, 6, 7, 8, 9 pigeonholes, whereas 10 pigeons. So at least one of these 9 pigeonholes must have at least 2 pigeons into it. So in one pigeonhole we may end up with 2 pigeons into it. So the pigeonhole principle states that if there are more pigeons than pigeonholes, then there must be at least one pigeonhole with at least 2 pigeons into it. So let's see how this pigeonhole principle is applied on the finite state machines. Suppose the string is a single A. The string length is 1. And to represent this string, the number of states needed in the finite state machine is an initial state Q0 with a transition labeled A goes to a final state Q1. So the total number of states needed is 2. Next, if a string of length 2, that is AA, string length is 2, so the number of states needed is 3. Same way for string AAA whose length is 3, so the number of states needed is AAA reaches the final state Q3, so the number of states needed is 1, 2, 3, 4, 4 states. Same, string AAA of length 3, actual number of states needed are 4. If the number of states available are less than 4, then we go for applying the pigeonhole principle, that is, some part of the string will be pumped back into the same state or it will go into a loop. Let us generalize with the statement. String is W, string length is M, say suppose M number of A's, then the number of states needed are M plus 1. But if the number of states available are less than M plus 1, then part of the string will be pumped back into a same state. So we can see here A1, A2, so on up to AI is the part of the string which is a prefix of the string which is to be pumped. Then Y is equals to AI plus 1, AI plus 2, so on up to AJ, part of the string will be which will be pumped back into Q1. Then Z string aj plus 1 to am is a suffix string which will reach the final state qf. So every string longer than the number of states must cause a state to repeat. So this is how the pigeonhole principle is applied on the finite state machine. So just now we made a statement that longer strings force repeated states. So let us see a theorem on it. Let m is equals to k summation delta SA be any DFSM. If m accepts any string of length k or greater, then that string will force m to visit some state more than once. That is, it will go into a loop if the number of states are less than the string length. So proof is, let m must start with in one of its state. Each time it reads an input character, it visits some state. So in processing a string of length m creates a total of m plus 1 state visits. If m plus 1 is greater than length of k, then by the pigeonhole principle, some state must get more than one visit. So if m is greater than or equal to length of k, then m must visit at least one state more than once. Knowing this principle, let us see the definition of pumping theorem for regular languages. The theorem states that if L is a regular language, then for some k greater than or equal to 1 and for all the strings which belong to L, where string length w is greater than or equal to k, then for some x, y, z, where w is parted into x, y, z, with the condition that the length of xy is less than or equal to k, y is not equal to epsilon, and for all q greater than or equal to 0, x y raised to qz belongs to L. So the proof, let us see the proof. If L is regular, then it is accepted by some DFSM. M is equals to k summation delta S A. Let k be equal to the length of k. Let w be any string in L of length k or greater. By pigeonhole principle theorem, to accept w, m must traverse some loop at least once. We can crave w up and assign the name y to the first substring to drive m through a loop. Then x is a part of w that precedes y and z is part of w that follows y. We show that each of the last three conditions must then hold. First condition is length of xy must be less than or equal to k. M must not only traverse through a loop, it can read k minus 1 characters without revisiting any states. But kth character will take m to a state visited before. Second condition is y must not be equal to epsilon. Since m is deterministic, there are no loops traversed by epsilon. And last third condition is for all q greater than or equal to 0, x y raised to qz belongs to L. Y can be pumped out once or in any number of times, and the resulting string must still be in the language. So this is what the pigeonhole principle applied on the pumping theorem states. So let's see the applications of pumping theorem. Pumping theorem is used to construct the proof by contradiction and prove that the language is not regular. The steps used are: first step is to assume that the language is regular. Then apply the pumping theorem for the given language. That is, choose a string W which belongs to the language and whose length is greater than or equal to A. If so, then split the string W into XYZ such that the length of XY is less than or equal to K and Y is not equal to epsilon. Now, choose a value wisely for Q such that X Y raised to Q Z does not belongs to L. Our assumption is wrong and hence by contradiction we prove that the given language is not regular. Let us see how to apply pumping theorem on a given language to prove that the language is not regular. So the first language given is A raised to n, B raised to n, where n is greater than or equal to 0. And now we are supposed to prove that the language is not regular. So first step is to assume that the language is regular. And choose a string W which belongs to L. So here we have chosen a generalized string A raised to K, B raised to K. And we must choose the string W such a way that the length of the string is greater than or equal to K. So the length of the string taken is A raised to K, B raised to K is 2K. 2K is greater than or equal to K. If so, then according to pumping theorem, we have to split W into X, Y, Z with two conditions: length of XY is less than or equal to K and Y is not equal to epsilon. Then according to pumping theorem, we have split W is equals to A raised to K, B raised to K is equals to A1, A2, so on up to AK minus 1, AK, K number of A's, followed by B1, B2, so on up to BK minus 1, BK, K number of B's, where check these two conditions. Length of XY, XY, X and Y parted, X and Y consist of AK number of A's, that is equal to K, and Y is not equal to epsilon because last A is assigned to Y. Then according to pumping theorem, the string X Y raised to QZ belongs to L for all possible values of Q, that is Q greater than or equal to 0. So now we must choose wisely the value of Q such a way that the string does not belongs to L. Let us see the first case. If Q is equals to 0, then W is equals to X Y raised to 0 Z. X is A raised to K minus 1 number of A's. Y is 0 occurrence. Z is K number of B's, that is B raised to K. This string A raised to K minus 1 B raised to K does not belong to this language because the language states that number of A's must be equal to number of B's, whereas in this string the number of A's are less than number of B's. Take one more case where q is equals to 2. Then w is equals to x y raised to 2 z. Then the string obtained is x consists of k minus 1, y 2 a's. So that is a raised to k plus 1 followed by b raised to k. This string does not belong to L because number of a's are greater than number of b's. Hence, by contradiction, we prove that the given language L is not regular. Let us see the next language. L is equals to 0 raised to n, where n is a prime number. We have to prove that this language is not regular. Possible strings in this language are 0 raised to 2, 0 raised to 3, 0 raised to 5, 0 raised to 7 and so on. So first step is to assume that the language is regular. Next, choose a string w which belongs to L. So we have chosen generalized string 0 raised to n which belongs to L and its length is less than or equal to n. So at present its length is equal to n. If so, then part the string xyz such a way that length of xy is less than or equal to k and y is not empty. So let us part the string w, that is 0 raised to n, as I number of zeros as x, j number of zeros as y which is greater than or equal to 1. Left over z is n minus I minus j number of zeros. Satisfying these two conditions, so length of xy is I plus j which is less than or equal to n and y is not empty. Then according to pumping lemma, x y raised to q z belongs to L for all q greater than or equal to 0. That is I raised to 0 raised to I, 0 raised to j whole raised to q, 0 raised to n minus I minus j belongs to L. That is I plus j into q, jq plus n minus I minus j belongs to L. So if we cancel plus I and minus I, we get n plus q, j is common here, j into q minus 1 belongs to L is prime for all q greater than or equal to 0. But if I take q as n plus 1, then what happens? Let's see. N plus j, q is replaced as n plus 1, this minus 1 as it is. So plus 1 minus 1 get cancelled, we get n plus jn. And if we take out n common, then left over is n into j plus 1 which belongs to L. But if j is equals to 1, then n into j plus 1, j is 1 plus 1 is 2. 2 into anything will nowhere be prime. So xy raised to qz does not belong to L. This contradicts the assumption that the language is not regular. Let us see the next language. L is equals to ww, where w belongs to ab whole star. We are supposed to prove that this language is not regular. So first step is to assume that the language is regular. Then choose a string w which belongs to L and whose length is greater than or equal to k. So the string chosen here is w is a raised to kb and next w is a raised to kb, which belongs to this language. and the length of this string is 2k plus 2, which is greater than or equal to k. If so, then part the string w is equals to xyz such that the length of xy is less than or equal to k and y is not equal to epsilon. So let's split w as a raised to k minus 1 number of x, 1a as y, and rest all, that is b a raised to k b as z. So let's see whether these two conditions are satisfied. Length of xy must be less than or equal to k. So here xy is a raised to k minus 1 plus a. So that is a raised to k. So length of x is less than or equal to k. So here it is equal to k. And 1a is assigned to y. So y is not empty. So according to these two conditions, when we have split this string, then according to the pumping lemma, this string is equals to x y raised to q z belongs to L for all q greater than or equal to 0. That is, w is equals to a raised to k minus 1, a raised to q, b a raised to k b belongs to L for all q greater than or equal to 0. Now let us consider case 1 wherein q is equals to 0. If q is equals to 0, then this string will be x y raised to 0 k, that is equals to a raised to k minus 1 as it is. Q is equals to 0, so this a does not occur. Then b a raised to k b. At this time it is not w. It means this string does not belong to this particular language. Or let's take one more case where q is equals to 2. Then the string is x y raised to 2z. That is, x is a raised to k minus 1. Y raised to 2 means total I have a raised to k plus 1 a's, followed by b a raised to k b. And again this string also does not belong to this particular language. Hence, by the contradiction, we prove that the given language is not regular. Let us see one more way of proving that the language is not regular, that is by using closure properties. Sometimes the easiest way to prove that a language is not regular is to use the closure theorems. Using intersection to force order constraints. For example, let L is equals to W, which belongs to AB whole star, where number of A's in the string is equals to number of B's in the string. If L were regular, then L dash is L intersection A star B star would also be regular. But L dash is what? A raised to n, B raised to n, where n is greater than or equal to 0, which we have already shown that it is not regular. So L isn't either. So let us see one more language on which we can apply closure properties to prove that the language is not regular. Language is A raised to n, B raised to k, C raised to n plus k, where n is greater than or equal to 0 and k is greater than or equal to 0. We are supposed to prove that this language is not regular. So first step is to assume that the language is regular. If the language is regular, then it is closed under homomorphism. So we can take h of a as a, h of b as a, h of c as c. Then the language can be reduced to a raised to n, h of a is equals to a, so a raised to n as it is. B raised to k, h of b is a, so b raised to k is replaced as a raised to k. H of c is c, so c raised to n plus k as it is. This is equivalent to a raised to n plus k, c raised to n plus k, which can also be written as a raised to m, c raised to m, where m is greater than or equal to 0. But this language, already we have proved that it is not regular. Hence, by contradiction, we prove that the given language is not regular. This is how we apply pumping theorem, which is based on the pigeonhole principle, to prove that the language is not regular. Thank you.